Welcome everybody to the second annual lightning round of the IEEE Robotics and Automation Society Agricultural Robotics and Automation Technical Committee. This is our webinar number 34. We are happy to have today a total of 31 presentations, down just one from last year, which was our first webinar, our first lightning round with 32. So we are in pretty good shape there. As a final reminder, please mute your phones or microphones right now. And with that, let's get started. When you see your slide, remember you have 1 minute to present, and we then move on to the next person. And Dave Anthony, you're our first guy.
All right, thank you, Marcel. My name is David Anthony, and I'm in Lincoln, Nebraska, where it's currently 1 in the afternoon. And so my research has focused on transforming UAV from a high-altitude aerial imagery platform to something that can operate very close to the tops of mature cornfields. And so why we're interested in doing this is we work with agricultural researchers who want to do things like get crop height information that they can't get from aerial imagery. And so by using a laser scanner, we can operate the UAV within 1 meter of the top of a cornfield and directly measure the height of the crop and canopy information over the entire life cycle of the field, which is giving our agronomy partners higher spatial temporal resolution data and information they can't get from their current sensing technologies. But it's difficult because we have to have more precise localization of the UAV than we get with traditional GPS-based guidance systems. So thank you.
Thank you very much. Paul, are you there?
Yeah, my name is Paul Bartlett. I'm at Near Earth Autonomy. I work with Marcel at this small company located here in Pittsburgh. I wanted to present here on our project on aerial phenotyping and precision agriculture. It's a nice continuation from the previous slide. So we're actually, it's being right now through a Department of Energy Terra program. So we're providing this aerial sensing and analysis pipeline to support higher speed breeding for sorghum for the purpose of serving as a new biofuel. So we're using these autonomous helicopters, 35, and we're carrying an ambitious payload of visible, thermal infrared, near IR, hyperspectral, and LiDAR. And then we're developing these the analysis pipelines to get the phenotype information out and find new indices and guide the breeding process.
Thank you, Paul. Gokhan, I just got a message from you saying you were having trouble connecting. Are you there? Okay, we'll get to Gokhan's slide at the end. Avital.
Yes, I hope you can hear me. My name is Avital Bechar. I'm calling from Israel. The local time here is 9 p.m. My field of interest are agricultural robotics, human-robot collaborative system in agriculture, precision agriculture, production engineering of agricultural processes, and sensor technologies for agriculture. I established the agricultural robotic lab 6 years ago. And I'm presenting here 4 projects, but I will have time probably for only 2. I will start with the development of a robotic sonar system for yield assessment and plant status evaluation that is shown in the left with the right orange background. It is in collaboration with Dr. Gabor Kosha and Professor Yossi Yovel from Tel Aviv University. The technology we are developing can evaluate the fruit mass on plant even if it is hidden inside the plant of or on the far side of it, or to measure the number of leaves on a plant. We can also see other rows and obstacles behind the row under investigation. The second yes.
Please wrap up 5 seconds.
Okay, so I will not have time to talk a bit more, but thank you.
Thank you. Okay, well, that is me. For those of you who don't know yet, I am no longer with Carnegie Mellon. I've been there as an engineer and faculty for 10 years. And now with Paul Bartlett and others, I work at Near Earth Autonomy, a small robotics company in Pittsburgh. We are developing a variety of systems from full-size cargo helicopters for autonomous delivery for the U.S. Department of Defense to full-size helicopters that can land on ships, all the way down to smaller aerial vehicles that can operate in urban environments safely without GPS, sensing and avoiding obstacles, indoor, outdoor, and being used for a variety of applications, including agriculture.
Peter Blok, Wageningen, 8:30 p.m. I'm working from Wageningen UR, AgRA Systems Research, and we are focused on precision agriculture and AgRA robotics. A good example of our work is the development of a selective and autonomous broccoli harvesting robot, which is in the left bottom. This robot uses machine vision to detect harvest-ripe broccoli while controlling a robotic XY frame. And besides this, our group is focused on field robotics, disease detection, and open field phenotyping for the public and private sector in Holland. Thank you. That's it.
Hi, just checking you can hear me.
Yes.
Oh, okay. Hi, my name is Marc. I'm calling from Sydney at 6 a.m. Work with a bunch of people, but on this particular project, it was Stephen Patiris and Salah Sukario. Top right-hand corner, you can see Ripper. It's a robot for going along vegetable crops. We had that in that picture. It's on a spinach crop. Down the bottom there, I wasn't allowed to put a video on apparently, so there's 5 pictures, space and time. So going from left to right, we can see this is our new system called Viper, and it's predictively shooting corn as it drives along with a very small dose of liquid. So between these two robots, we're capable of autonomously navigating vegetable crops and identifying targets and hitting them with a small dose of fluid automatically. And the idea is to hopefully go commercial with some of these systems pretty soon. So we're getting more away from the research and trying to get into the commercial end of the spectrum with these particular systems. Thank you.
Peter? Peter, are you there? Okay, we'll go back to Peter again.
My name is Lars Grimstad. I'm a PhD student at the Norwegian University of Life Sciences. I'm in Ås, just south of Norway, where it's currently 8:15 p.m. The last year, our group has been working on building and testing our new robot, Thorvald, which is a powerful, lightweight, and low-cost agricultural robot. It has a 4-wheel drive and 4-wheel steering, runs ROS, designed to be used with exchangeable tools, and has a mass of approximately 170 kilos. In the pictures, you can see Thorvald driving around in our research farm. So together with our master students, we are now working on the second version of Thorvald, and our goal is to build 2 or 3 of the new robot during the first half of this year. And also last year, some of the master students designed and built a precision seeding tool for Thorvald, and we needed then conducted a small experiment on seeding patterns for wheat, where we compare traditional row patterns to a more uniform pattern. And our results suggest that a more uniform pattern is better for suppressing weed. Thank you.
Joris IJsselmuiden from Wageningen. It's 8:15 p.m. From the Farm Technology Group. Am I loud enough?
Yes.
Okay. We have been doing agricultural robotics research for many years. In the top, from left to right, you see a sweet pepper harvester and a cucumber harvester below it, and a leaf removal for cucumber. Then to the right, we have a robot for detecting and weeds in a sugar beet field. Below that, we have a robot for collecting floor eggs. And then we have, more to the right, some more agricultural robots. At the bottom, you see a master-slave tractor system, and, well, some more examples. In the bottom left, I put some pictures from a new project that will be starting soon, which is called Saga, Swarm Robotics for Weed Mapping and Control, in which we will use a swarm of UAVs for weeding purposes. And in the bottom right, another new project of ours, which has just started, which is about robotics and vision research by a garden trimming robot. Thank you.
Avi, are you there?
Yeah. Can you hear me?
Yes.
Avi Kani, Tel Aviv, Israel, 9:15 p.m. We are developing fresh fruit harvester robotic system built from a multi-robotic system, 3D image sensor, and RGB in order to identify the fruit we want to pick. We integrated the system using the ROS, and we integrated the system with Watch innovation to use the tube patent in order to transfer the fruits into the bins. Next year, we will have the first commercial system available.
Yeah. Thank you.
Good morning, everybody. Do you hear me?
Yes.
So this is Manus Karki from Wageningen State University. Right now it is 11:40 in Pacific time zone. I work also in agricultural robotics. Very good continuation from the presentation we saw from Avi a moment ago. Robotic apple harvesting has been one of the major areas for my research and development over the last several years. In addition to that, I do automated pruning. I saw another presentation earlier about human-robot collaboration. That's very similar to what we do too. I also work in robotics or automated dairy harvesting, as well as weed control projects that are also similar to a few presentations earlier. UAV also is another area. I work in bird deterrence with UAV. With that, thank you very much, and we'll be happy to mingle around after the presentation.
Oh, yeah.
Do you hear me?
Yes, Jay.
Hi, my name is Jay. I'm from University of New South Wales in Sydney, Australia. It's 6 a.m. here. What I present here is something that I presented last time, just an extension into the commercial world. What you see on the top left is the original research that we did. We have developed a fully autonomous seeding system which can plant seeds very precisely. And then this has now progressed into commercial version, which is what you see on the top right. It is in fact a spraying machine. And on the bottom left, you see the user interface, which allows the tractor to survey the land itself. It can survey various different zones. There could be obstacles, speed zones, spray zones, and so forth. So the research has now completed to commercial level, and what we are now working on is force-controlled machines for plant-level care in broadacre farming. Thank you.
I just would like to remind everybody to please keep their lines muted. Someone has been speaking in the background that disturbs the speakers. Thank you. Dr. Khan, are you there? We'll go back to Dr. Khan at the end.
Yes, my name is Rick van der Zedde. Can you hear me?
Yes.
Okay, I'm a senior researcher and also business developer. I'm located in Europe, in the Netherlands, and it's about 8 o'clock in the evening. So I work at the Wageningen University and Research Center, and two of my colleagues have also presented their work. So our group is focused on computer vision, applied to vision-guided robotics in agri-food. And we are mainly working on the level of like individual plants or individual food objects. And our research is very focused on how to link with industry. So my colleague Gert Kootstra and I have prepared this overview of our work. And my quest is actually to connect research to the needs of industry and to set up research projects together. So if we look at the left, the robotic quality inspection, that is something that is really needed in industry. A lot of fruit and vegetables need to be controlled or inspected on quality, and we are working on robotic modules to do the automated inspection. In the middle, pick and place, there's also like the replacement of human labor, how to grasp a vine tomato and put it into, for instance, a consumer package. Below, there's a robotic device able to actually produce small pot roses in horticulture. Quality inspection
Rick.
of tomatoes is another thing. Yep.
I have to ask you to wrap up in 5 seconds.
No problem. And the last thing is phenomics. That's plant phenomics, has been mentioned before by other colleagues. We've got quite a lot of research groups working on plant phenotyping. Thank you.
Thank you.
Hello, this is Cheryl McCarthy. I'm from the University of Southern Queensland at the National Centre for Engineering and Agriculture. We have an automation, robotics and machines vision team consisting of 13 mechatronic, electronic and software engineers and 5 PhD students.
The print was kind of weird, the way it was.
Our background is in machine vision systems. We work closely with farmers in industry-funded projects to develop systems that retrofit to existing machinery or could be used as a component for a robotic system. Our project tooling consists of automatic surveillance, big data, adaptive control, augmented reality and automation and control for applications in weed control, pest and disease scouting and irrigation management. We have 2 patent applications for real-time machine vision-based weed discrimination, and we're also developing low-cost vision systems that are robust in sunlight, and we are in our research agreement with John Deere. So we've got images there showing various projects showing different apparatus and machine vision systems.
Thank you, Cheryl. Come on.
Yes, I'm here. Hello,
Yeah.
everyone. Can you hear me?
Yes.
Oh. Hello, everyone. My name is Saman. I'm calling from Iran. 11 o'clock p.m. I'm currently working at the University of Ramin Agriculture and Natural Resources University, and our current projects are real-time monitoring of performance of the tractor. In this system, we continuously collect the data with a frequency of 1 millisecond and actually monitor the forward speed in this first project. Speed of all wheels, fuel control, and parameters such as plant something in the shop and you use the spindle on the other side.
Saman, we are losing you.
No. Do you have me here? Can you hear me?
Yes.
Okay. In the second project, we are monitoring broader waste image analysis. In this system, we use HNV method to remove a head and the tail of the chickens in order to improve the accuracy of the system. Second project, we use a quadrotor to actually measure the
spindle can be pushed or pulled away, damaging the
in the sugar beet industry. And in the last project, we monitor the seed trajectory in order to find out the performance of the seeder, the online system. The first system and the last system could also connect to the internet and send the data.
I'm gonna ask you to just stop there, okay?
Okay.
Thank you.
All right. Good afternoon. Good morning. My name is
Now we have.
Marcel, can you hear me?
I can hear you, Steve, and I've been trying to get the people who keep talking to just be quiet, but I'm not sure exactly how to do that, and I think we are in better shape now.
Okay.
So, Steve, please go ahead.
All right, yeah. So my name's Stephen Nuske. I am a researcher at Carnegie Mellon University in Pittsburgh, in the U.S. So I do a lot of work in developing computer vision systems for a variety of different agricultural applications. So we work with a number of different plant scientists and looking at a set of different applications you can see here. One is in precision viticulture, trying to collect lots of different types of information and control the growth of vines to optimize yield and quality goals. We're also looking at a project on plant phenotyping that Paul and Marcel talked a bit about before, and also pushing now further into harvesting and using computer vision systems in harvest systems. Yeah, so that covers it a bit. All right, thanks.
Good evening, Timo Oksanen, Aalto University, Finland. Time is 9:30 p.m. We are located in southern Finland and temperature right now is minus 18 Celsius. We have been working with isopas technology since 2003 and we have demonstrated with a couple of prototypes tractor implement automation, and if we start from top left going down, you can see first one seed drill, then no-tillage seeder and combined fertilizer and seed drill, then mower. The next one is kind of safety demonstrator for idea that to implement command tractor, then a harrow, sprayer, one fertilizer spreader, a landscape blade with 8 degrees of freedom, and as you know, in our country we use tractors also wintertime for snow plowing. We did automation for that, and silage wagon and acid applicator for that. Thank you.
Hi, it's Jim Ostrowski from Blue River Technology in Sunnyvale, California. It's about 11:30 a.m. our time. So we're a technology startup company based in the Bay Area. With our goal is to use computer vision robotics to make every plant count, to do kind of individual plant level decision making and actions. We've started by building a lettuce thinning machine, which is pictured there in the top kind of center. That we have 6 of those machines we've built. We operate as a service every day, do over 150 hectares a week. It runs 18 seed lines, 6 kilometers per hour with high accuracy. Our fleet does about 1 million lettuce plants an hour, so it's a pretty high throughput system. And we're currently building the next gen machine to do more general weeding applications and for other crops and apply other materials. We also have secondary projects in phenotyping. As other people have mentioned, we have a ground-based system and an aerial system. In particular, the ground-based system, we've been showing high 90%, 97, 99% accuracy in stand count, as well as full 3D reconstructions of plants. So we're continuing to utilize that and work with breeders, some of the top breeders in the U.S. for that. Thanks.
Hi, this is Dejan here from Deep Field Robotics, Bosch startup from Germany. We're currently working on a machine for automated outdoor field testing, also phenotyping. It's a ground-based machine, basically with a 2D and a 3D sensor that drives over the field autonomously and essentially counts plants for the germination rate and basically measures them in 3D, so measures the 3D area as well. Our system is end-to-end, so we basically drive over the field, acquire the data, localize, detect plants, and classify them, and also bring them to you in a cloud, so that you can analyze them in a web-based application. In the future, or this is the roadmap, basically towards the herbicide-free weeding, where we'll basically use the detection and classification results from the phenotyping part of the project and apply it to the mechanical weed killing. If you have an excellent work in any of these areas that I just talked about, and you especially plan to commercialize it, please get in touch with us. We're also offering open positions. Thank you.
Hi, I'm Zach Pesamenti from Carnegie Mellon at the National Robotics Engineering Center, where we work on a variety of commercial and government projects, including several in ag. The one that I'm showing here is a USDA project where the main idea is to take some of the extensive work on pedestrian detection in urban environments and apply it to the rather neglected off-road and specifically agricultural domain. So we've got a tractor or truck equipped with stereo cameras as our only input, and the general approach is illustrated in the diagram at the left. The part of the work that I think will be of most interest to this group, though, is the associated data set, which we plan to release publicly. So a few example images are shown, as well as stats on the number of labeled frames of video available, which is still growing. And these videos show people in different orchards in a wide variety of controlled poses and motions, including even like people on ladders and stuff. Varied clothing, occluded but to varying degrees by trees and weeds, and with all the lighting and other challenges of real outdoor data. So we plan to give an AgRA TC seminar when we release the data set, and please email me with any comments or questions. Thanks.
Hello, this is Santosh Petla. I'm calling from University of Nebraska-Lincoln. So we have currently around 4 projects in the machine automation area. The first one is a multi-robot system. We are trying to develop control strategies for cooperative behavior among machines. And we're using these red machines at the top to simulate those behaviors. And the other project that we are working on is CAN data collection from the tractors while they're operating in the field, so that we can better characterize the power requirements of tractors for different field operations. As you can see, there is some of the data that I presented there, and these are the actual fuel use rate and power delivered by the tractors in the field. So we want to use the same information to use those load cycles on the future robotic machines. And one of the machines you see is a flex row. This is a 40-horse machine. There should be gasoline engine over hydraulic transmission. And we want to use this machine for multi-purpose. And that is why we're thinking about building a flexible height and flexible width. It's going to be. And also the wheels can be done 90 degrees at the end of the row, so that we can have benefits in terms of the field efficiencies.
Santosh, I can ask you to wrap up in 5 seconds.
Okay, so the last one is a within row crop following robot. Can sense the corn population. Yes.
Hello, can you hear me?
Yes.
Great. My name is Tessa Pocock, and I work at the Smart Lighting Engineering Research Center at Rensselaer Polytechnic Institute in Troy, New York, and it is 2:35 p.m. and -8 degrees Celsius. I've set up a plant physiology lab that's integrated well into the engineering school here, and we are actually using the dynamics in narrowband LED lighting to develop light algorithms to modulate one of the 26 biochemical pathways that can be induced by light. And you can see this in the photograph of the lettuce, where we have the same cultivar. The only difference here is the spectral ratios, and you can induce the nutritional content of the plant. We're also developing a real-time chlorophyll fluorescence sensor and methodology that eliminates the need for dark adaptation or saturating pulses, in order that the plant's physiological state will regulate the light environment. And you can see our homemade version there under ERC in that bottom left-hand picture. Thank you.
Okay, can you hear me?
Yes.
Yes.
Okay, great. Well, my name is Gerrit Polder. I'm also from the University of Wageningen in the Netherlands. I'm from another group, from the Greenhouse Horticulture Group, but we work close together with the colleagues who presented before me. The project I'm showing here is the first one on the left is an EU project. It's Sweeper. It's the development of a sweet pepper harvesting robot. And the goal is to get to a commercial device, to commercial prototype, I have to say, within 3 years. On the right, you see a 3D light field system on a robot system which works in the greenhouse. It's for large-scale phenotyping in greenhouses for large plants like tomato or peppers or cucumber. We use light field technology to get color and depth information together. We also work on hyperspectral imaging for disease detection in the field and in the lab. Trimbot project is already mentioned by Joris. And then we have the pick and pack, which is a food processing line, which can be adapted to several foods and packaged together. And we do the coordination of the whole line here in Wageningen. So thank you.
Julio, are you there? Julio or Milela? Okay, we have 2 slides from the group. We will go back to them towards the end. Dave, are you there? Dave Reiser? Looks like we've been missing some people from Europe at this time. How about we go to Marc in Australia? Marc, do we have you? Okay, towards the end, we seem to be losing people by the bunch here. How about Steve?
Can you hear me?
Yes.
Yeah. Okay, great. So my name is Steve Young, and I'm at Cornell University. Is 39, and it's snowing outside, so we're not doing anything in the field. But this really doesn't have to do with field work because what I've been working on, or what people have been working on, is the kind of the conceptual side of this. So a lot of these talks have been on the tools, which is great. But if you look at what we're doing, trying to identify what's happening in the whole field of integrated weed management. So if you look at the figure on your left, you'll see a continuum where there's moving from low-level traditional precision to true integrated weed management, and all that is possible because of the automation and the recognition that we can now do things across spatial temporal frames, scales. On the right is our outreach, so our center, we are a communications center, and we have a signature program in advanced production systems, and really the focus is on a lot of the work that's being done that you've heard about today. So visit our website, send me an email to talk to you, and thank you.
All right, we come to the end. I want to first of all thank everybody for presenting. I want to check if there is anyone online, on the phone or on a microphone, who did not have a chance to present. Please let me know if you are there and you did not present.
Hello, can you hear me?
Yes. Who is that?
Okay, this is Giulio. Giulio Reina from Italy.
Okay,
yes.
Giulio, your slide is on. You have
sorry. Yeah, sorry. Okay, so good evening, everyone. I'm Giulio Reina from University of Salento. We are located here in the hill of the Italian booth. So we are kind of far from, can you hear me? It's okay? Connection? Yes.
Yes,
hopefully
yes, you have 1 minute.
so we are far from the cities and the main industrial centers, but we can enjoy beautiful sandy beaches, and agriculture is one of our main source of economy. So there is a large interest in the technological transfer from robotics technology to the agricultural field. We got 2 consecutive grants funded by the European Union. The ambient awareness for autonomous agricultural vehicles, that is over. And January 2016, we started a new project, simultaneous safety and surveying for collaborative agricultural vehicles. Part of the projects are DTI from Denmark, Fraunhofer from Germany, Istea from France, and Class Agrosystem that made available the tractor you see on the left, which we outfitted with many sensors. Some results, you can see some results. For example, these results are coming from stereo vision, and one of the partner was CNR. Those are the results coming from stereo vision. Specifically, we developed a multi-baseline stereo frame, as you can see on the left of this slide. It is composed by 2 trinocular systems, so we can enjoy the short range and the long range, as you can see on the right. One of our goals is environment awareness of intelligent agricultural vehicles. So specifically here we are trying to differentiate between traversable, drivable ground from non-ground. Again, improving both the accuracy and the field of view of a traditional system using multi-baseline, multifocal stereo system.
Thank you, Giulio. Thank you very much.
Okay, that's it.
Is there anyone else who did not have a chance to present? Gokhan, we did not get you. Are you there? Peter Frolic, also we had trouble reaching you. All right. If anyone else who did not have a chance to present, let me know. Before we go to some questions and some discussion, I want to show you this slide from Amy Tab. This is a teaser. Amy, unfortunately, was not able to join us, but she is giving the webinar next month. Therefore, you're going to get a full presentation of her work in determining shape of fruit trees for phenotyping and pruning. Dave, I see that you're writing here your microphone is broken. I'm sorry to hear that, but we have your slide, and we'll have you give a webinar in the near future. Anyone else that we missed today? Okay, very good. Here's what we saw today. From California at 11 a.m. to Australia at 6 a.m. on Friday morning. Lots of ground vehicles, aerial vehicles. I don't think I saw any aquatic or underwater vehicles, so maybe that's another domain for our group to attack. We saw a lot of manipulation. We saw a lot of technology for fruit detection, weed detection, autonomous spraying, autonomous weeding. We had job offers for the first time in the history of the SBC. That's always welcome, of course. So we have a new thing here, job offers on the webinar. And that shows how strong and active and vibrant the TC is. So again, thank you everybody for participating. I also want to let you know that we reached a peak of 41 people at the top of the webinar, which is now a record for the TC. So the next people giving webinars throughout the year now have a new bar to reach of 41 people. With that, let me open up for questions, see if anyone wants to have any questions. Let's see, Julie, you're saying I can speak for Marc if he's not there. He is not here, and let's put Marc's slide on. Julie, go ahead. Julie, are you there?
Yes, I'm here, yes.
Okay, go ahead. You can talk on Marc's slide.
So you are giving me more time?
No, I'm asking Julie Tang from Australia.
Okay, so it's not me, sorry.
Oh, no, that's okay. Julie Tang, she's saying she can present for Marc, but somehow we can't hear her. We'll do it next time, Julie, don't worry. Any questions or comments from anyone? For the time being, I'm going to leave the webinar on, and I see a lot of conversations on the chat window, so let's just let it go.
Marcel, can I take a moment, just 30 seconds to briefly remind about the conference?
Absolutely.
Hey everybody, this is Marc again. You have received my email or Marcelo's email about Agricontrol 2016, the conference in sensing, automation, and control for agricultural applications. It's going to be in Seattle in August 2016. I would very appreciate your presence there and submission to the conference. If you have any questions, I'm sure the conference will be one of the very appreciated and very much relevant to what we do as a group in this group here. So again, I'll appreciate your presence and submission to that conference. And if you have any questions, I'm always there. Thank you.
Manoj, there's a question here. If it's that AgRA 2016, can you please clarify that it's a different thing?
It is Agricontrol 2016. It is available at isac.wsu.edu.
Please put that on the chat window. Thank you. Well, thank you again, everyone, for being up, especially the people in Northern Europe and Australia. And our next webinar is on February 11th with Amy Tabb from the USDA, talking about her work on phenotyping and pruning. Everybody have a great day and or a good night.